Right now, in whatever room you're in, your metabolism is already several steps ahead of you. Long before your first coffee, before you've even fully opened your eyes, hormone levels are shifting, your liver is adjusting its output, and a countdown that started hours ago is about to hit a critical checkpoint. Most people think their metabolic day begins with breakfast. It doesn't. It begins the second consciousness returns. And what happens in that first hour sets the tone for almost everything that follows. Over the next 30 days, 5 separate morning habits stack on top of each other, and by the end, you'll see exactly which ones actually move the needle on metabolism and which ones are just noise. Stay through to the end, because the day 30 results aren't what most people expect. Sleep doesn't end the way most people picture it. There's no switch that flips from off to on the instant your eyes open. For roughly the last 90 minutes before natural waking, your body has already been quietly preparing for departure. Body temperature starts climbing from its overnight low point, and the brain's master clock, a cluster of around 20,000 neurons called the suprachiasmatic nucleus, starts sending out wake-up signals to nearly every organ system at once. By the time you're conscious enough to register the ceiling above you, your liver, your adrenal glands, and your pancreas have already received the memo. None of this requires effort or awareness from you. It happens whether you get up at 5 in the morning or 11, whether you eat breakfast or skip it entirely. But the timing and consistency of when this cascade fires off turns out to matter a great deal for how well the rest of your metabolic day unfolds. And the first domino in that chain is a hormone almost everyone has heard of, but almost nobody understands correctly. Cortisol has a public relations problem. Most people associate it exclusively with stress, anxiety, and things going wrong in the body. But there's a specific healthy cortisol surge that happens every single morning in virtually everyone, and it has nothing to do with a bad day. Researcher Jens Prusner and colleagues first documented this phenomenon in 1997, naming it the cortisol awakening response. Within the first 30 to 45 minutes after you wake up, cortisol levels rise by anywhere from 50% to as much as 160%, according to work by Angela Clow and colleagues published in 2004. That's not a stress reaction. It's a scheduled biological event. What throws this system off isn't cortisol itself, it's inconsistency. Waking at wildly different times from day to day, or being jolted awake by an alarm in the middle of a sleep cycle, appears to blunt or distort this response in ways researchers are still working to fully map. And here's where it connects directly to metabolism. Cortisol influences how sensitive your tissues are to insulin. A well-timed, healthy morning cortisol spike sets up favorable conditions for the hours ahead. A chaotic one doesn't. Which brings up the next question. If hormones are already responding to something as simple as consciousness returning, what happens when you add actual sensory input, like light, into the mix? In 2014, Catherine Reed and colleagues at Northwestern University published a study in PLOS-1 that tracked light exposure, sleep timing, and body mass index in 54 adults over a full week using wrist-worn light sensors. What they found was striking. The earlier in the day someone received their light exposure above 500 lux, noticeably brighter than a typical indoor room, though still well below outdoor daylight, the lower their body mass index tended to be. This relationship held even after accounting for physical activity, calorie intake, sleep timing, and age. Getting bright light later in the day was linked to a higher body mass index instead. The mechanism behind this comes down to how the suprachiasmatic nucleus actually receives its instructions. Specialized cells in the retina detect light and send that signal directly to this master clock, which then uses it to synchronize the timing of secondary clocks located throughout the body. In the liver, in fat tissue, in muscle. Every one of those tissues runs on its own local rhythm, and light exposure is one of the primary cues that keeps them all pointed in the same direction. Miss that morning signal, or send it at the wrong time of day, and those peripheral clocks can start to drift out of sync with each other. It's worth being precise about what this research does and doesn't show. Reed's study is observational. It shows a strong association, not proof that morning light alone causes weight differences. Other research has found that intense artificial light exposure during a meal can acutely affect insulin response regardless of time of day, which is a separate and more specific finding. But the consistent pattern across multiple studies is clear enough. Your circadian system is listening for light every morning, whether you're paying attention to it or not, and that timing appears to ripple outward into how your body handles energy for hours afterward. Here's where a lot of assumptions about breakfast start to fall apart. In 2018, researcher Elizabeth Sutton and colleagues published a study in Cell Metabolism involving men with prediabetes, comparing an early eating window, all meals finished by early afternoon, against a standard eating pattern spread across a normal 12-hour day. The early eating group showed meaningfully improved insulin sensitivity and better function of the pancreatic beta cells that produce insulin. And this happened without any weight loss at all. The metabolic improvement wasn't a byproduct of losing fat. It came from when the food was eaten. This doesn't mean skipping breakfast is inherently harmful, and it doesn't mean eating the instant you wake up is required either. The research here is about the position and consistency of the eating window relative to your internal clock, not about any single meal in isolation. What it does mean is that two people eating identical food in identical amounts can end up with different metabolic outcomes purely based on when that food shows up relative to their own circadian rhythm. And that rhythm, as it turns out, can be nudged by something as unglamorous as a glass of water. In 2003, Michael Boschman and colleagues published a study in the Journal of Clinical Endocrinology and Metabolism that measured something deceptively simple. What happens to resting energy expenditure after a person drinks 500 milliliters of water? Using whole room indirect calorimetry, a method precise enough to detect small shifts in how many calories the body burns at rest, they found that energy expenditure increased by roughly 30% between 30 and 90 minutes after drinking in both men and women. The mechanism isn't about the water itself carrying energy, since water obviously has none. Boschman's team traced it to what they described as an osmosensitive response. Essentially, the body detects the sudden change in blood plasma concentration caused by absorbing that volume of water, and this triggers activation of the sympathetic nervous system. When the researchers blocked beta-adrenergic receptors with a medication called metoprolol in a follow-up study, the thermogenic effect disappeared almost entirely, confirming that this pathway runs through the same nervous system network responsible for the body's fight-or-flight responses, just at a much smaller scale. Scaled up, Boschman's team estimated that drinking around 1.5 liters of extra water per day could increase energy expenditure by roughly 200 kilojoules daily. That's a modest number on its own, not a dramatic metabolic overhaul, but stacked on top of a well-timed cortisol response, properly synchronized light exposure, and an eating window aligned with the body's natural rhythm, it starts to look less like a standalone trick and more like one piece of a much larger coordinated system. And that raises an obvious question. What happens when someone actually moves their body during this window, instead of just drinking a glass of water? 5 habits down, 6 left to go. Quick question before we keep moving. Out of everything covered so far, the cortisol spike, the light exposure, the meal timing, the water, which one are you already doing without even realizing it? And which one have you been getting completely backwards this whole time? Tell me in the comments. I actually read them, and the next block is where the payoff starts showing up. There's a specific reason morning movement feels different from an evening workout. and it comes down to what's already circulating in your bloodstream at that hour. After a full night without eating, insulin levels are low and liver glycogen has been partially drawn down. Under those conditions, the body defaults to burning a higher proportion of fat for fuel rather than carbohydrate because there's less circulating glucose competing for use. A systematic review and meta-analysis published in the British Journal of Nutrition confirmed this pattern across multiple trials. Exercise performed in a fasted state consistently showed higher fat oxidation compared to identical exercise performed after eating. This connects directly to insulin sensitivity. And here's the broader link this pattern feeds into. Researcher Brett Goodpaster and colleagues, publishing in the journal Diabetes in 2003, found that increases in fasting state fat oxidation among people with obesity were the single strongest predictor of improved insulin sensitivity following a structured activity program, accounting for over half the variance in the results. Insulin sensitivity in that study improved by an average of 49%. The two systems, how efficiently the body burns fat while fasted, and how well it responds to insulin, appear to move together. For decades, brown adipose tissue was considered biologically irrelevant in adult humans, something that mattered for infants and hibernating animals, but not for grown adults. That assumption collapsed in 2009 when Wouter van Marken Lichtenbelt and colleagues published a study in the New England Journal of Medicine showing that healthy adult men have metabolically active brown fat that responds directly to cold exposure, visible and measurable through imaging technology. Unlike ordinary white fat, which stores energy, brown fat's entire job is to burn it, generating heat by activating a protein called UCP1 inside its mitochondria. What makes this relevant to a 30-day window is a follow-up study by Takeshi Yonashiro and colleagues, published in the Journal of Clinical Investigation in 2013. Subjects with low baseline brown fat activity were exposed to 2 hours of mild cold around 17 degrees Celsius every single day for 6 weeks. Brown fat activity increased in parallel with a measurable decrease in body fat mass, and the two changes were directly correlated with each other. A separate study by Anouk van der Lans and colleagues, also published in 2013, found that meaningful increases in brown fat-driven heat production showed up after just 10 consecutive days of cold acclimation, suggesting this tissue can begin remodeling itself well before the 6-week mark. Here's a distinction that gets lost in most morning routine advice. Waking up at 5 in the morning isn't inherently more metabolically beneficial than waking up at 8. What actually seems to matter is whether that wake time stays consistent from one day to the next. Researchers use a specific term for the mismatch between someone's sleep timing on work days versus their days off, social jet lag, and it's measured as the difference between the midpoint of sleep on free days compared to scheduled days. A 2025 analysis by Sabag and colleagues, published in Sleep Science and Practice using data from the National Health and Nutrition Examination Survey, found that social jet lag was associated with a significantly higher likelihood of metabolic syndrome among adults who were otherwise getting a normal, adequate amount of total sleep. In other words, these weren't sleep-deprived people. They were people getting enough sleep, just at inconsistent times. The association held even after adjusting for age, sex, education, and other lifestyle factors. Though it's worth being clear this is an observational finding, showing an association rather than direct proof of cause and effect. This ties back to everything already covered. An irregular wake time doesn't just disrupt how rested you feel. It appears to blunt the cortisol awakening response and desynchronize the timing signal your eyes send to the master clock, which then ripples out to the light-sensitive, meal-sensitive, and temperature-sensitive systems already discussed. A consistent 7 a.m. wake-up, repeated daily, seems to do more metabolic work than an inconsistent 5 a.m. wake-up, chasing an idealized optimal hour. Which raises a practical question. How long does the body actually need to lock in these adjustments before they start showing up as real, measurable change? A single fasted walk, one cold shower, or one well-timed morning doesn't restructure anyone's metabolism. These systems respond to repetition, not isolated events, and the research gives some useful markers for how long that repetition needs to run before changes become measurable rather than theoretical. A helpful comparison point comes from jet lag research. The circadian system typically resynchronizes at a rate of roughly 1 day per time zone crossed, meaning a full realignment after a significant schedule disruption can take a week or more even under ideal conditions. Morning routine changes function similarly. They're essentially asking multiple internal clocks to shift their alignment, and that doesn't happen instantly. It's worth being precise, rather than making this sound like a universal switch that flips exactly on day 7 for everyone. Different systems adapt on different timelines. Brown fat remodeling showed up around 10 days in that particular study, while the insulin sensitivity improvements from early time-restricted eating research were measured after several weeks of consistent practice. The honest pattern across all of it is this. Meaningful physiological change is rarely visible in the first few days, tends to become measurable somewhere in the second week, and continues building well beyond that if the behavior keeps repeating. Everything covered so far has been about signals arriving from outside the body. Light hitting the retina, water hitting the stomach, cold hitting the skin. But there's a parallel system running entirely inside individual cells, built from a small set of genes that essentially keep their own private clock, independent of but coordinated with the master clock in the brain. The core mechanism involves 2 proteins, clock and BMAL1, which pair up and switch on a set of other genes called PIR and CRY. As PR and CRY accumulate, they loop back and shut down clock and BMAL1's activity, a self-regulating cycle that resets roughly every 24 hours in nearly every tissue in the body, including the pancreas. Researcher Biljana Marcheva and colleagues demonstrated just how much this matters in a 2010 study published in Nature, an animal study using mice, worth stating clearly since the findings don't automatically transfer to humans. When the clock and BMAL1 genes were disrupted in these mice, the animals developed hypoinsulinemia, abnormally low insulin, and went on to develop diabetes. The pancreatic islets, it turned out, run their own self-sustained circadian rhythm of gene activity, independent of the rest of the body, and disrupting that rhythm was enough to cause disease on its own. Human evidence points in a similar direction, though through a different kind of study. Jelena Stamenkovich and colleagues, publishing in the journal Metabolism, Clinical and Experimental in 2012, examined actual pancreatic islet tissue donated by people with and without type 2 diabetes. In the islets from donors with diabetes, expression of the clock genes PAR2, PAR3, and CRY2 was significantly lower than in non-diabetic donors, and lower expression of these genes correlated with reduced insulin content. This is observational tissue data rather than a controlled experiment, so it shows association rather than proof that disrupted clock genes directly cause diabetes in humans. But combined with the mouse findings, it paints a consistent picture of a molecular clock inside the pancreas itself, one that appears to care very much whether your mornings are consistent or chaotic. Here's where all 11 pieces come together, and where it's worth separating 2 very different categories of change. Some of what's been covered resets almost immediately if the behavior stops. That morning's cortisol awakening response is a single-day event tied to that specific waking moment. Skip a consistent wake time tomorrow, and tomorrow's response shifts accordingly. The thermogenic boost from drinking water fades within roughly 90 minutes, according to Boschmann's measurements. A single morning of bright light exposure doesn't permanently fix a circadian clock. It's a daily nudge that needs repeating. Then there's a second category, the changes that appear to accumulate and persist because they involve actual physical remodeling rather than a temporary hormonal blip. Recruited brown fat tissue, built through weeks of consistent mild cold exposure, doesn't disappear the morning after a single warm day. Improved beta cell responsiveness and insulin sensitivity, the kind measured in Sutton's early time-restricted eating research, reflects a change in how efficiently pancreatic cells are functioning, not a same-day fluctuation. And trained peripheral clocks, the liver, the fat tissue, the pancreas all firing on a synchronized schedule, represent a structural realignment, not a mood. So what actually happens to your metabolism after 30 days of fixing your morning routine, based on everything the research shows? It's not a single dramatic transformation. It's a stack of modest, individually unremarkable adjustments, slightly better insulin sensitivity, a bit more active brown fat, better synchronized internal clocks, a healthier daily cortisol pattern that only becomes significant in combination, sustained day after day. Individual results genuinely vary depending on starting point, consistency, and which of these 11 habits actually get followed through. But the underlying biology is clear. This particular hour of the day carries far more metabolic weight than most people ever give it credit for. If this changed how you think about your mornings, hit like and subscribe. It genuinely helps this channel keep producing research-backed content instead of recycled wellness advice. And if you know someone who's been chasing quick fixes instead of understanding what's actually happening in their body, send this their way. Thanks for watching all the way through.